Dominic Baril is a PhD student in our lab. He did his undergrad study in mechanical engineering in Sherbrooke University. For his final project, he worked with the company Exonetic on a robotic arm, and he's now in the lab since, I forgot how many times, how much times,
1 year and
2018,
a
I guess,
half.
one year and a half. And he did his transition from accelerate transition from master to PhD, and he's now working on control for unmanned ground vehicle. And that's about it. I will let him present from now.
All right, so I will start sharing my screen. So can you guys see, just to make sure, can you guys see the presentation and the tiny laser pointer?
Yes.
Okay, perfect. So I will start now. Thank you all for taking the time to attend this webinar on the article that we submitted to this year's conference on computer and robot vision that took place back in May virtually due to the COVID situation. The article is entitled Evaluation of Skid Steering Kinematic Models for Subarctic Environments. It was submitted by me and the precious help of 8 of my colleagues. I will name them now. So there was me, Vincent Grondin, Simon-Pierre Deschênes, Johan Lacombe, Maxime Vaidis, Vladimir Kubelka, André Galland, Philippe Gigard, and François Pomerleau. So thanks again for your help to all of these guys. Many of them are here today. And I hope I can give you a good summary of what we did for this article. So first of all, I wanted to show you a quick video showing what are the objectives for our research program related to control. So I will just show you this quick video so you have an overall idea of what are our objectives and why do we do this. So we all remember that infamous Montreal car crash video. So what we ask is what happens in winter conditions and how can we solve the robustness issues that arise when we drive in winter conditions or harsh or complex off-road conditions. So as we can see, the robot tends to get stuck, and our goal is to allow the vehicles to be autonomous even though it's navigating in, for example, deep snow or crossing a snowbank, for example. And the last objective is to do the deployments in the worst possible conditions to robustly thoroughly validate the algorithms that we study. So this article was published, linked to a research program that was started by the lab, one of the lab professors, François Pomerleau, and the project is called SNOW, or Self-Driving Navigation Optimized for Winter. And the goal of the project is relatively simple. The goal is to adapt the autonomous navigation pipeline to harsh winter conditions. So we could break down the autonomous navigation pipelines to 3 main components, namely localization, path planning, and path following. This presentation will be linked to control, therefore linked to path following. And also for this project, for experimental validation, we deploy a ClearPath Robotics Warthog unmanned ground vehicle, which is a alpha-ton robot in the Montmorency forest that belongs to Laval University, with the goal to make deployments in the most unstructured, dynamic environments that we can create. So we have a thorough robustness evaluation of our and the state-of-the-art algorithms. So first of all, how can we model a mobile robot? A mobile robot can be modeled the most simplest way as a body frame of reference that is defined with its origin located at the center of the robot's body, with the x-axis pointing towards the forward direction of the vehicle. That navigates into a world frame. So the world frame here is defined in red. And the goal is to have the reference frame follow a desired trajectory that is here defined in black. Such systems can be modeled with a general differential equation, a nonlinear differential equation that's shown here. If we break down this equation, we can see that the model formulation is defined in the F component. So this is a nonlinear motion model that will allow to compute the variations in the state vector. The state vector for a mobile robot is typically composed of the position and orientation of the robot in the world frame. It requires an input vector, which constitutes the command that we send to the robot. So basically, for example, with the car, the steering angle and the wheel velocities that we ask for it to get. And also, lastly, the model requires some model parameters to allow the model to generalize to various platforms or various environments, which is the case for our research project. So overall, our objectives for the control part of the SNOW project, we split the objectives into two main theoretical objectives. The first one is to implement and increase the robustness of the state-of-the-art motion modeling techniques. So these techniques, what they aim to do is to improve the accuracy that we can get when we define a model formulation as F, and how we manage to tune and track the model parameters to allow models to be as accurate as possible. And then the goal is to use these models with the state-of-the-art path following techniques in order to increase the robustness of these techniques to more and more gradually more complex situations. Also, the goal for all of this, those two objectives, is to do a thorough experimental validation and analysis of what we get when we deploy those algorithms with a full-scale platform in a fully unstructured environment. Today, the goal of the presentation, also since it's the beginning of my PhD, the goal is to focus on motion modeling techniques. So the following presentation and the article was solely based on motion modeling techniques. Why is a motion model so important? I'm going to try to explain it to you through the following small figure. So let's imagine we have a mobile robot that is driving, for example, on a concrete road here. And we have next to the road some relatively narrow and filled with obstacle snowy path that will lead to the goal that we would like to get to with our vehicle. For example, we would like to pick up some logs, or we would like to go rescue someone who's stuck at this goal. So the first step would be to plan for a trajectory that is shown in blue here that will allow our robot to get to our goal. And then our second step would be to follow this trajectory. So first step, as long as we drive on roads, we might have tuned our model properly for the road conditions. And the path following algorithm will probably work quite well on the ideal conditions that are like the road-like conditions. However, if we get to the point where we change terrain type, for example, here we're going to maybe cross a snowbank and start rolling in snow, the traction conditions are probably going to change. And if we keep sending the same values as if we're driving on concrete, we have a risk to not properly follow the defined trajectory and maybe hit obstacles when the paths become more narrow. So that's something we definitely don't want. So if we had a model that was able to account for the change in the change in traction conditions, for example, the robot doesn't turn as smoothly as when it was driving on concrete, we could have planned for different commanded inputs to allow the vehicle to have a better path following performance when it switched terrain type. So it would be more robust to this type of change in terrain conditions. And then it will allow us to get to our goal safely without hitting any obstacles with our vehicle. So the fundamental element of every motion model for mobile robots is constituted of the steering geometry that we use for our vehicle. This consists of how the vehicle is constructed and how can we send commands to the vehicle in order to get it to change its orientation or go forwards or turn whatever we want to do with our vehicle. So I've shown you here on this slide 3 of the what we think are the most popular steering geometries that were explored in the literature. Of course, there are many more. However, we focused on these because they are the most widespread ones, and also they allow us to get a good idea of what the steering geometry looks like. So the first one I will show you is the differential drive robot. This robot is constituted of 2 wheels and a chassis, and we're going to send commands that will modulate the speed of the wheels on each side that will allow to go forward and turn with our robot. As an example for this robot, we have the Roomba robots that we use to clean our homes automatically. If we take it a step further, we have a very similar steering geometry, but which is more complex due to the fact that the skid steering geometry has 4 wheels instead of 2 wheels. And we have 4 wheels here, but it could be 4 or more wheels. So we could have an 8-wheel skid steering geometry, or even full tracks that go to the full length of the robot side. So the skid steering geometry is very similar to the differential drive geometry due to the fact that it uses the same input vector. So the wheels on the left side will be commanded to go to a certain velocity. The same will be done with the right side wheel velocities. And that's what's going to allow us to steer and go forwards or turn with our robot. The added difficulty here is that oh, I will admit someone else to the room. The only added difficulty here is that since the wheels are separated from the center of rotation, there is going to be added skidding with the vehicle. We're going to give more details on that on the next slide. And lastly, we have the Ackerman or car-like vehicle. This is probably the most well-known steering geometry. How we turn with this vehicle is slightly different. The wheels are typically going to go all at the same wheel velocity. However, to turn, we're going to define a steering angle that is given by the phi variable here. This vehicle type is very useful. However, for our project, we use the skid steering geometry. Why we do this? The first reason is that it has robust and simple driving mechanics. So since the front wheels don't need to turn, we simplify the drivetrain, and that allows us to have a more robust platform. Also, it has very high maneuverability on complex terrains. And lastly, this platform type allows for zero radius turning, so the robot can turn on the spot, and that allows it to be more efficient when driving off-roads. However, this vehicle type has some very high inherent skid sliding dynamics, and those dynamics are very hard to model. And this is the subject of the article that we sent to CeRVIM. As you can see, when the robot drives, it tends to go sideways a lot when it tries to turn. That's the part that's difficult to model. So we took a look at the literature related to robot deployments in winter conditions. And as you can see in all of those pictures, those robots tend to be deployed in relatively large and open areas in winter conditions. So those areas, they don't require such an accurate motion model. And that's why we saw that there was no literature that was specifically made to work on motion modeling in snowy environments. So that brings us to the contributions that we proposed for our paper. So for this paper, we analyzed 5 kinematics from the state of the art for skid steering mobile robots, which we will call SSMRs for the rest of the presentation. First, we evaluated their fitness for a heavy platform. So our robot is alpha ton, which is much more than what is done in the state of the art. Also, we evaluated the performance for each model on snow-covered terrain. And lastly, we highlighted the impact of angular motion to the motion prediction error that we get from our models. So for this article, we focus solely on kinematic modeling for SSMR motion. Why do we use kinematic modeling? We have 2 main reasons. The first one is that such models are much more robust to wrong parameter identification, because an error in a certain parameter can be accounted for into another parameter. So basically, the parameter identification doesn't require such accurate values. And also, such models don't require any inertial information about the platform. And this kind of information is usually hard to get from the platform manufacturers. So what does a kinematic do? A kinematic model do, sorry. What it does, we see in this equation, is it computes the time derivative of the robot state. So basically the velocity of the robot body. So basically we have the velocity towards the X body axis, the Y body axis, and the angular velocity along the Z axis. So basically the yaw velocity of the robot. And this model is defined as a kinematic model that will compute the body velocities values based on the wheel velocities on each side of the robot, as explained with the input vectors previously explained. In other words, what we do with our model is we give an estimation of the rate of change of the states. Why is it an estimation we call? Is because the models will never give us really accurate values. This is limited because the only input we have for the models are the wheel velocities, and we need much more measurements to get an accurate measurement of an accurate estimation of the robot's position. So in this paper, what we did for the formulation to make it to simplify the explaining the differences between the various models is we define each model as a Jacobian matrix that will link the input wheel velocities to the rate of change of the body velocities. Each Jacobian matrix includes some model parameters that need to be identified. So we will give, in the next slide, we will give an overall idea of all of the models and what parameters need to be experimentally identified. So the first model that we present in the paper is a relatively simple model and still a very popular model. It's the ideal differential drive model. So we take the differential drive geometry that we explained before, since it's a relatively simple geometry, and we get the following Jacobian matrix. Without going too much into details, the main parameters that are important for this model are the wheel radius and the wheel baseline, which is the distance between the contact points for the two wheels. And for this kind of model, the robot will continuously turn on an instantaneous center of rotation that is defined here. And that center of rotation is based on the forward velocity of the vehicle and the angular velocity of the vehicle. So the first model that is specifically defined for skid steering vehicles is an extension of this aforementioned differential drive model. So what Mando and other authors have suggested in 2007 is that for a skid steering robot, the contact points of the wheels on each side of the robot with the ground have a different instantaneous center of rotation than the one of the whole robot body that was also presented in the differential drive model. So these contact points are found through geometric analysis, and I will spare the whole geometric analysis. You can get it in detail if you look at our paper. We have defined it, but for this presentation, I will cut it a bit shorter. So the position of each of those centers of rotation, which are all located on the same axis, are what composes the parameters of the model. And for this model, they have also added two wheel slip parameters. So we have an alpha L that defines the wheel slip on the left side and an alpha R that defines the wheel slip on the right side. So those are the parameters that come into account for this model. For the same model in the same paper, they have also made an analysis that if the axis that includes all of the instantaneous center of the rotation of the vehicle is parallel to the y-axis of the robot's body, frame, we can, and also the distance between each center of rotation for the wheels and the origin of the robot's body frame is the same. So basically the centers of both sides are symmetrical. We can make the assumption that the model is symmetrical. And that basically brings us back to the ideal differential drive model, except that we add two parameters that will need to be experimentally evaluated. So basically, we have a new estimated baseline of the robot. So we basically say that the robot might be larger to account for losses in rotation motion, in angular motion. And also we add a wheel slip parameter alpha that is supposedly the same for both sides of the robot. And the distances between the center of rotation are modeled through the Y0 parameter that gives the estimated baseline. So for this symmetrical model, Wang and other authors in 2015 have experimentally found a relation between the distances between the centers of rotation of the robot's wheels and its the center of the robot body frame. They have found this relation between this distance, and that adds some beta 1 and beta 2 model and lambda model parameters that we need to experimentally find. So basically, this model now has three parameters. So this is another model that we presented in the paper. And lastly, the most kind of conceptually simple model is presented by Anuzaki and other authors in 2004. This is a simple but complicated to tune model. The model is a Jacobian that is only constituted of model parameters that need to be experimentally found. So there is no physical properties linked to these parameters. You only need to find them through optimization. So for all of these model parameters, we need to have an efficient way to compute them, or at least find optimal values for them. So how do we do this? If we take back our mobile robot that is located, for example, on completely snowy terrain and even snowy terrain, at time t0, what we're going to do is make a model prediction for the displacement of the robot that is shown in red here. So from t0 to t1, the robot should, based on our model, do about this displacement. Then we drive the robot and we take a measurement with our localization algorithm that can be done, for example, with GNSS antennas or vision-based localization algorithms. So we will compute the actual displacement of the robot. And then we're going to use the following equation to compute an error between the prediction and the actually measured state of the robot. So basically, we compute the difference and we multiply it by itself when transposed. The covariance matrix here is there to be able to compare translational errors with angular errors, because the full state also includes the orientation of the body. So the goal of this matrix is just to put all of the values in the same unitless value. What this equation gives us is a scalar value for the approximated error of the model prediction. And that approximated error can be summed throughout the whole trajectory. So now, for example, the robot is now in the T1 position that we measured with our localization algorithm. We can make another prediction, drive the robot, make another measurement, and then once again, we can use the same error equation to maybe sum up the error for the entire trajectory. For this paper, what we did is we just summed up this exact error throughout the trajectory, and we used an optimization algorithm that was aimed to minimize this error scalar. So basically, this became our objective function. One important notion that was introduced through these figures is the horizon. So basically, the distance between where the robot is and where the model is actually compared with the ground truth. This horizon for this example is shown basically in time, but the horizon can be defined spatially. So for example, for this example, we have maybe 6 seconds between the robot position, the prediction, and when it's compared to the ground truth. But this could be 2 meters, for example. For this paper, we used a spatial horizon because it allows more numerical stability for when the robot is idle. Sorry. So for the experimental evaluation of all of our models, not just evaluation, but also model training, what we did is we used our platform and we drove it on two distinct terrain types. So the first one being dry concrete in an underground parking lot located at the PEPS of Université Laval, and another one being snow-covered terrain located at the Grand Axe of Laval University. So what we did is we drove 2 kilometers on both of these terrain types. We drove two separate trajectories, one being for the model training, so to get the right model parameters, and another one being for the model evaluation. So in order to use the trained values of our models to get an idea of the performance of each model on the same terrain type. What we did when we drove the robot is we maximized the input excitement. So basically, we tried to get as many input wheel velocities as possible. And finally, for all of these experiments, we used the iterative closest point or ICP algorithm for localization. This algorithm uses point clouds as input and computes the rigid transform between the point clouds of two positions of the robot in order to produce an odometry with centimetric accuracy, which is much, much better than what we get from the model prediction. Therefore, it's a very interesting algorithm to use as ground truth for the tuning our models. And another interesting part of the ICP algorithm is that it produces some maps. As we can see here, we have a 3D map of the underground parking lot environment. We can see the pillars, we can see the walls. And in red, we can see a part of the ground truth trajectory that was generated. And also we can see another map of the snow-covered terrain area that we drove in with the same ground truth of part of the trajectory. So for the results, the first interesting result is that in this figure, we have trained the models on various training horizons. So basically the length of the window that we use for model training was changed for each color. And what we can see is very interesting. We can see that when a model is trained on relatively small horizons, for example, the first two one at 0.5 meter and 1 meter, those models tend to perform better than other longer trained horizons for smaller horizons, which makes sense. However, when a model is trained, for example, at a longer training horizon, it tends to be more stable as the evaluation horizon becomes bigger and bigger. So what we take away from this figure is that the training horizon should be defined based on what application we want to do with our model. For example, if we want to do path planning with our model, we would need to have a model that is trained on a relatively large training horizon because it's going to allow us to plan for a long trajectory. However, if we want to do control or highly responsive model predictions, we would like to train our model on relatively smaller horizons. So now we have for every 4 of the 5 models presented above, we have the result for the model prediction accuracy. We didn't present the differential drive model in these because its error was quite higher than the other models, simply based on the fact that none of the model parameters, as we remember, it only used the wheel radius and the wheel baseline, are based on wheel-ground interactions. Therefore, the model is not trained with the specific terrain and has a much higher error. So we can see on the x-axis of both figures, we have every different model. In red, we have the error on concrete, and in blue, we have the error on snow. And on the left side, we have the relative translational error, and on the right side, we have the relative angular error. So what we can see, what we can take away from there is that most models tend to perform quite similarly, except for the fact that both the extended differential drive asymmetric model and the full linear model tend to have a better translational prediction performance. And we attribute that to the fact that it's the two only models that can account for lateral motion of the robot's body. And also we can see that the extended differential drive symmetric model tends to have a better angular motion prediction performance than the other models, which is also an interesting result. Also, we took the extended differential drive asymmetric model and analyzed where did the errors come from. So we tried to evaluate the error the translational error based on input parameters, and we didn't see any real correlation. However, if we try to evaluate the relative angular error based on the input vector. So on the y-axis, we have the right wheel velocities, and on the x-axis, we have the left wheel velocities. We can see that when the difference between both wheel velocities gets gradually higher, so basically on the yellow areas here, that means that the robot tends to turn. So if we have a large difference between wheel velocities on both sides of the robot, that makes the robot turn more. We can see that there is a much higher angular prediction error related to our models. So when we implement such models, an really important thing to take into account is that much of the error will come from eye turning scenarios. So last result, and that's my personal favorite that we got out of the paper. It's not even related to any specific model. What we have on the x-axis here is the commanded angular displacement. So basically how much we ask the robot to turn for every specific windows. And on the y-axis, we have the measured angular displacement. And as before, in red, we have how the robot behaved on concrete, and in blue, how the robot behaved on snow. So we found this result quite interesting. First of all, because we can see that the measured angular displacement is higher on snow than on concrete for the same commanded angular displacement. That's interesting. That basically means that the robot turns better on snow. We didn't see this coming. It kind of surprised us. But when we think of it, it makes sense for the reason that when the robot is driving on snow, it tends to the rotational motion tends to be due to the terrain being deformed under the wheels. However, when driving on concrete, which is very hard, the terrain does not deform, and it basically becomes the wheels that have some deformation. So that wheel deformation is a bigger friction component than the actual terrain deformation. Also, we can see that when driving on snow, we have a much higher nonlinearity factor. That's going to be interesting to take into account in future work. And lastly, we computed the interquartile range for both of these distributions. It's shown in the relatively hollow area. And this allows us to see that the interquartile range is typically higher on concrete than on snow. So that means for a specific commanded angular velocity, we have more possible values when driving on concrete than on snow. So that means there is more uncertainty to the motion when we drive on dry and hard terrain. So this is it for the paper's result. For future work, we're going to want to work on dynamic modeling to take into account the friction between the wheels and the ground and maybe inertial components. Also, we're going to want to, instead of tuning the parameters offline and reusing them for another trajectory, we want to be able to have online tracking so our model become adaptive, as we suggested in the figure where the robot drives from road to a snowy path. That's going to allow us our model to be more robust. And lastly, we want path following that will be robust to complex conditions, such as snowfall and immobilization that is due to navigating in deep snow. So lastly, thank you for taking the time to I will be happy to answer any questions. And also our paper is available on our website, which you can find at norlab.ulaval.ca. If you want, just do a Google search for Norlab robots and you will find them. And also you can search Norlab on YouTube, Facebook, and LinkedIn to see our latest results, which we keep posting on there as we go along. So also I wanted to share the references that we used for this presentation for winter deployments and the kinematic models that were presented in the theoretical section. So thank you, and I will be happy to answer any questions.
All right, thank you, Dominic. We are still at 19 participants, which is good. Is there any questions from the audience?
I tried to open my chat so I can see them too.
So I will start by to point out interesting fact with that publication is that we published it to CRV, and eventually that paper won the best paper for robotic vision, and everybody was confused, so they renamed the prize only for Dominic's paper. So now he wants the best robotic paper for that conference instead, because clearly there was no or not much vision in it. So we have a question from Julien.
Yeah, hi. Thank you, Dominic, for the presentation. I missed the beginning, but I think I got a good glance of everything. Had a few questions or well, ideas, and I don't know if you thought about that. Well, it's very interesting, the difference between concrete and snow. And I think your analysis is good. That's probably the friction of the snow being much less, it's easier to skid steer. And for what was interesting is on concrete, I was expecting to see a much more precise line. So your variation is interesting, and I was wondering, do you think it could be the temperature as your tire warms up, their properties change? So that's something maybe could be interesting to investigate. So tire as they warm up, they get softer. So probably that could be something that could explain. And on snow, what's interesting is you're pretty sure that your tire will stay cold. So that could help you in terms of predicting what's happening. So that's one thing. And then I have a second question, but maybe you explained it at the beginning. I'm not sure, but have you thought about using, as your model, one of your models in linear, have you thought about using Kalman filters and something, where you can have a faster parameter variation in your modeling? So
I think that's a very interesting question. You're actually pointing towards our future work. So this is a very, very good question. If I could just get back to the initial slide, even though the models are defined as Jacobian, so basically linear relations between the wheel velocities and the robot's body velocities, all of those, in order to get the actual displacement of the robot, we have to compute the transform between the body reference frame and the world reference frame. So those rotation matrices make the models become nonlinear all the time. So even though we start with a really simple linear model, we always explode to a nonlinear model. But that doesn't prevent the state of the art from using Kalman filters. What they do is they linearize the dynamics, and they use extended Kalman filters to track the model parameters. What we find and our idea for future work is that linearizing those dynamics might not be enough to account for really large parameter variations. For example, if you drive on the road and then you want to cross a snowbank, your tires are going to start spinning like really freely in the snow, and you're going to try to almost immobilize. Your robot is probably going to be immobilized in the snow. And to account for like those very large parameter variations, what we want to do maybe is to work on more advanced parameter tracking, or to allow the robot to find which motion mode it might be in. Or so it's a very good idea to use Kalman filters. It's what the state of the art does to track model parameters. And what we want to do next is to make it super robust to large parameter variations.
I may add, for the heat building up on the tires, that's true that we didn't do a temporal analysis, and we should go back and dig into that. Something that is sure is that this robot is made for off-road driving, so the pressure in the tire are very low. so that we can climb over rocks. And I think we have pictures of that eventually we should add. But when we turn on spot, the wheel essentially bend, so it gets stuck on the concrete, and the whole tire bend for close to 10 centimeters. Sometimes you have the feeling that just the tire will tear apart because the friction is so high. So for sure we are building heat in that thing, but maybe faster than what you think. So it might be that in the few minutes we already saturated the heat that the thing can hold. But that's indeed a good point. And that was the whole message about all of those kinematic model with fixed parameters, is that the wheel are actually moving on the ground. So the contact point on the ground is moving quite fast actually because of all of those deformation. And of course the tires are most probably stiffer on ice and would just slip. So maybe more stable because of that.
This is interesting because, well, as you just said, the high deformation. Then, if I don't know if you you know those brush model of tires, but at high deformation, the behavior change because you have full slip under the tire. Well, when the deflection is not that great, you have a part that slip and the other one that grip. So that could be interesting to investigate. But I think your model was quite linear, so probably that's not the case. But for the snow, it's something quite similar to that. So maybe it's a brush model-ish because, well, it's more the snow that deflect than the tire. But that's very interesting.
I think where your expertise with model deformation or model behavior for the tire level becomes really interesting is when we try to look at dynamic modeling, where what they do is they try to model for a force vector that will be at the exact wheel level and then export it to the body reference frame so that you can transform a tire level model to the whole body for every wheel. That would become really interesting to look at because you can just add the different wheel friction model and try to see what it does to the whole body behavior, and then evaluate it with localization algorithm that is very strong expertise in our lab.
Yeah, indeed, yeah.
And something we figure out is that the models that we find in the literature, even 2017 is not that old, are super simple. The contact point are simplified. Now if we have 4 contact points there, they assume that it's a single track, and everything is super simple actually. And there's now we have the computing power to actually take care of that properly. The question is, do we gain 1% or do we gain 20% on the accuracy? Okay, is there any question from someone else? Otherwise, I can go back to Julien or ask another question. Okay, I will try something. So in your videos, you're showing a robot with 4 wheels and then with tracks. Do you foresee any change, or what do you think will happen? If I recall well, you did this paper with tires. What do you think will happen if we change and put 4 tracks? Do we need to retune everything? Do we need to re-experiment, or?
So basically, it's a very good question. When acquiring the platform, we have also acquired tracks for the simple reason that tracks have a much better maneuverability in soft terrain. So basically, when we go to really deep snow, the tracks are going to allow us to navigate where the wheeled robot would just get stuck. So that's why we got those tracks. Of course, the model parameters will be drastically different when changing from the wheels to the tracks. So there are 2 areas that might be much different when using the tracks. First off, if we imagine the robot is in the air and not even moving on the ground, The tracks are much higher, require much more energy to get turning. So the actual powertrain dynamic model of the tracks will be really different, without even talking of the wheel to ground interaction. And the second one is exactly that. The tracks with the ground, they will behave really differently. And this is why in the lab, for the next part of the experimental evaluation of all of our models, we're building an automatic calibration program that we can launch with our robot before, for example, doing an off-road mission at the forest. So the robot will autonomously drive itself and try to stimulate the input variables in order to be able to tune itself. So as we go along experimentally, our goal is to be able to take any robot and make it drive itself, and after that do a model tuning to get good initial values for our models. And then the goal is to be able to track the motion parameters. So when the robot, for example, if it starts on concrete and then goes to deep snow, we want to be able to be robust and adaptive to this kind of change in behavior.
All right. Is there any questions for the audience? I see that we are getting close to lunchtime.
Maybe just a small comment from me. I guess, did we try it or did we discard the idea that we could train all those models, then chop them in half? Because in your plots, the angular part was better for some and the translation for some. Could we have just chopped them in the middle and used the better parts? Or would that break actually the training part?
Since the training uses the whole state, it could maybe be more difficult, but I think where your ID becomes interesting, if you recall sorry, I will get to the actual slide of the error computation. If we recall the error computation formula, we remember that there is a covariance metric that is used to put all of those translational and angular values to a common unitless value. We could actually use the covariance metrics to increase the importance of the angular motion in model parameter training. So that might be a way to actually get some models more robust to angular motion. But you're also right that maybe combining asymmetrical models with symmetrical models asymmetrical models, they behave better on with the translational prediction. Sorry, if as we can see here, the two models here are asymmetrical. So we could use those models to predict the translational displacement, and then use a symmetrical model to predict only the rotation of the robot. That's a good idea. I didn't think about that, but that could be something that we look into.
On the other hand, since we already have full linear model, which is just was it like that? We were training a matrix, all 6 numbers there independently. That already probably should be able to cover these 2 models.
Mm-hmm.
Just training was not so easy to get because in this plot you can see that the full linear is good for translational part, but quite fuzzy for rotation. Yeah, my idea of chopping those 2 models, since they are linear, we should be able to express that by the full linear, but just taking the numbers.
Otherwise, the state of the art, where they kind of highlight the error sources, it's been related to wheel acceleration and not wheel velocity. So you could extend the input vector to take into account wheel accelerations. And such models, they also add dynamic models to reason with the wheel friction on the ground, and not just generalize it to a whole body geometric relation. So you add computational complexity, your model takes longer to compute, but usually it gives more accuracy. That's what the state of the art is doing, like the 1 or 2 last years.
It's true that with just linear models, as was mentioned before, we are kind of chasing ghosts here, because those 6 numbers are definitely not enough to capture, and there also are so many influences from the environment which we don't take into account at all.
All right. So I would give the last word to Annette.
Okay, well, thank you very much, Dominic, for your presentation. In the coming 2 weeks, là, je sais pas si je devrais parler en français ou en anglais. In the coming 2 weeks, we will have seminars from Institut Intelligence et Données, IID. So next week, it'll be Professor Jacques Corbeil from the Faculté de Médecine. Il a une chaire en génomique médicale. And the following week, Professor Philippe Després, Faculté des Sciences et Génie. Il se spécialise en imagerie médicale. Il parlera des sciences des données responsables dans le domaine de la santé. So the next 2 weeks will be EED. And you're welcome to join these webinars if you wish.
Thank you.
Thank you. See you all.
Thank you for
Bye.
attending.
Goodbye.
Thank you very much.